So we're going to continue into describing sets. So I have a supplemental video that I'm going to include in the lecture area that's a little bit more of an in-depth look at sets. This is kind of not as mathy, but a little bit more with the education mindset. So I'm also going to post the other one for you to take a look at. So set language and structure is going to be applied to elementary mathematics, connections between finite sets and whole numbers, as well as the one-to-one correspondence. So in the years from 1871 to 1884, we have something called set theory that emerges on the mathematical scene. And set theory is kind of the concept that there are things grouped together by similar characteristics. And these groupings are kind of a primary way that we teach children to understand numbers. So we're going to define a set as any group or collection of objects, and the objects that belong inside of the set are called elements or members of the sets. Those terms can be used interchangeably. One method of showing what's inside of a set would be to list them in brackets and or braces, and then label them with a capital letter. Each element of a set is only listed once. So for instance, if the number 2 occurred more than one time, if I'm listing the elements, I would only write it once. The order of the elements isn't important, so they don't have to be written in a specific order. The symbol that we use to represent that these elements belong to this set would be this E for element. And if they don't belong, we're going to use the E with a slash. So a set has to be well defined. We must be able to tell whether or not an object belongs to the set, so it has to be clear what the characteristics or the grouping factors are. So if I have these sets in C, I have colors, I have natural numbers, I have lowercase letters, so they're all kind of grouped together and they're listed as a roster. The ... means it continues in the same manner. If I wanted to use set builder notation, I would say that set E is all values such that, so the bar is such that the elements of n and that are x is less than 11. So I'm looking at elements of natural numbers that are less than 11, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if I wanted to write these in set builder notation, here in A I have even numbers, so you can just use words to say even numbers, or you could say 2 times n. Same thing with odd numbers. I have multiple ways I could represent them. For elementary education, the easiest way is going to be able to teach students to just say that's a grouping of odd numbers. If I want to list out the elements, I would plug in the values given for k. So I have this grouping of 2k plus 1 such that k is 3, 4, or 5. So I'm going to make my table and plug in 3, 4, or 5, which means my set is 7, 9, and 11, which results from this over here. If I want to write the set B in this manner, if I look at positive, even natural numbers less than 8, that would be 2, 4, and 6. Two sets are equal if and only if they contain the same elements. The order of the elements makes no difference, and if they're equal, I can write A equals B. If A does not equal B, then there is at least one element that does not belong to both groups. One-to-one correspondence means that I compare my elements so that for each element of P, there are exactly one element of S, and vice versa. We call this one-to-one correspondence. So if I have a set 1, 2, 3, it can be replaced with one-to-one correspondence by giving pairings of those things written in order. There are multiple ways to arrange this, depending on the order that you write things in to establish a one-to-one correspondence. So if we want to list all the possibilities, we could do that in a table or in a tree. If I want to know the exact number there, we can be sure that given one element, we'll have another element that would be A, B, or C. So a number is going to be matched to a letter. Once we've paired an element, that leaves 2 additional elements for the second set to pair with the number 2. And then there's only one left for the number 3. So the way that I can figure out the number of ways is by doing m times n. So if two sets are equivalent, there exists a one-to-one correspondence. So let's say I have a set of 3 and 3. If there is a set of 3 and 3, then the first slot has 3 possibilities, the second slot has 2 possibilities, and the last slot has 1. So that I have 3 times 2 times 1, which is 6 different ways that I could write that set. So let's start starting to compare these sets. Each set is both equivalent and equal to itself. Sets A and B are not equivalent. Notice I have different groupings of letters here. Set B and C are equivalent but not equal because they have the same number. And sets B and D, if you look at D, it's just written in a different order than B. So they are equivalent and equal. So cardinality is given as the number of values within a set. So if they ask you what is the cardinality, you're just counting the number of items in the set. So we have 5, 1, 0, and then this is the empty set, so we'd have 0. And for this one, x equals x plus 1 is never going to be a true statement. If I have 2 equals 2 plus 1, that's not true, which is why that set is also 0. A set is finite if its cardinality is either 0 or a natural number, a counting number. Here are some examples. An infinite set is not finite. That's where the ellipsis comes in. Or something like 2 equals 2, 3 equals 3, x plus 1 equals x plus 1. There's an infinite number of things that I could replace in there to get that answer. The universal set would be everything that could possibly be grouped under that consideration, and we usually save the capital letter U for this. So if I have the universal set is defined as x the member of the U.S. Senate, then I'm going to use my capital U to be a universal set, and my particular sets are going to be indicated inside of a rectangle. So here's my Venn diagram. So U would be everything inside of the rectangle. And then I'm going to consider subsets of this. So if I have X, it's a female senator, so I have a circle for females that lies inside of my rectangle for a universal set. If I'm looking at the set of all members that are not female, that would be everything shaded outside of the circle. And in this way, this brings us to the idea of a complement. A complement is kind of like a contrapositive. It's not. So if I have B and I want to find not B, well, not B would be A and B. It's in the same grouping, but it's not in B. So it's found here in the universal set, but it doesn't belong to B. If I say not universal, there's no such thing. And the empty set would also belong to universal. Here, if I look at not S, so then I want a zoo animal that is not a snake. Here, if I want not E or not O, my universal set is all natural numbers. So not E would be things that are inside of O, or not O would be things that are inside of E. Because this is even numbers, not even would be here. O is my odd numbers, so not odd would be a part of E. And if I'm looking at subsets, my subsets are written with this notation. And so if it's not a subset, we would just draw a line from it. So that's two different ways. It's an underscore, and it's kind of like if something is a subset, the values in the subset are also found in the overarching life set. So for something to be a subset, then every element of B has to also belong to A. So we would draw this as here's my universal set. Everything inside the rectangle is in my universal set. Then I have this group of things in A. So maybe A is the alphabet upper and lowercase, and then B would just be the lowercase. Well, A has all the lowercase values, so B goes inside of it as a subset, and it belongs to the universal set of letters. So in order for this subset to be true, there has to be at least one thing in A that is not in B. So in our example, capital letters, there's multiple capital letters that would not fall into set B. Here's an example where we have numbers. If I look at the subsets here, B is a subset of P when I plug in. B is a subset of A. B is a subset of B. And B is equal to B and P is equal to P. So when I'm saying P is a subset of P, it's basically saying you have equal statements. Now, let's suppose A and B are finite sets. So they have a definite end. If A is equal to B, then the number of elements in set A has to be equal to the number of elements in set B. If A is a proper subset, then the number of elements in A should be less because we need that one that doesn't belong to A. So if I look at A and B are infinite sets, I have the natural numbers here starting with 1, the natural numbers here starting with 0. So what I notice is that 0 does not belong to set N. So I do have one number that is not present. So even though I have this correlation, it's still possible to establish a one-to-one correspondence by letting each element correspond to a number in W that is smaller, so that we can say that N is approximately W. So in general, if there are so many elements in a set, then 2 to the n subsets could be formed. So if I have 10 elements in a set, I could have 2 to the 10th subsets. And that's all this slide is telling you, is to use that formula.